Okay, welcome back everyone. In this video we're going to wrap up our discussion of one-dimensional kinematics by looking at free fall. So we're going to try to figure out how we can solve problems involving straight line motion with constant acceleration. And in this case, free fall is in the downwards direction. So free fall is what we use to indicate that an object is falling under the influence of gravity, with gravity being the only force. Now it turns out that free fall can also refer to when an object is moving upwards, but we'll get to that later. So gravity is going to accelerate the object the entire time it's in its flight, and near the surface of the Earth, we're going to say that the acceleration due to gravity has a magnitude of 9.8 meters per second squared, and the direction is down. For now, we're going to ignore air resistance, and in a little while, when we do forces, we will consider a couple of different types of air resistance and look at how that affects our motion. And we're just going to do a couple of example problems, and that's pretty much it. So before we do that, let's just recap what's going to happen to our 1D motion equations when we introduce that the acceleration is gravity. So we had that velocity as a function of time was v initial plus acceleration times t, and now we have the same thing, but we're going to replace a with g, and we're going to say that g is 9.8 meters per second squared downwards, which means that most of the time we will be replacing it with negative 9.8, depending on the direction the object is moving. Likewise, x of t is x naught plus v naught t plus 1/2 a t squared, and the only change here is that, again, acceleration is going to be replaced with g, and again, the same context. So on to this example. We have a student who tosses her keys vertically to a friend in a window 4 meters above, and the keys are caught 1.50 seconds later. So that's our time, and that is our delta y. So that's the other change, is that instead of x of t, what we might say is that we have y of t. And instead of x naught, we'll talk about y naught. Okay, so this means that delta y is going to be equal to 4. And here's a useful tip: delta y, or delta anything, is always final minus initial. So we can write it like that. So if we want the initial velocity, v naught, that they're tossed with, we can try and set up our equation here. So y of t, or y final, is equal to y initial plus 1/2 gt squared plus v initial times t. And I wrote this in a weird order, but it'll work out. 4 is y final, because y initial can be set to 0. Then we're going to do plus 1/2 negative 9.8 meters per second squared and 1.5 seconds plus v naught, oh, that's squared, times 1.50 seconds. Now, it's important to draw a diagram when you solve problems like this. So v naught is upwards and the acceleration of gravity points downwards. And we're going to say that upwards is positive. Okay? And also it's traveling in a positive direction for its delta y. All these things put together give us the fact that v initial is about 10 meters per second. And you can check this, but basically you're going to take 4 and you're going to be adding to that 1/2 times 9.8 times 1.5 squared, and then dividing all of that by 1.5 to get v naught. And what was the velocity of the keys just before they were caught? So v final is equal to v initial plus gt. So if v initial is 10, g is negative 9.8 meters per second squared, and t is 1.50 seconds. So that's going to be negative 4.7 meters per second, which suggests that the keys went up and now they're back on their way down. And that's because of this time of 1.50 seconds. It turns out that there's actually 2 times when the keys are at this height. And we're going to see more about that in the next example. So in this one, a ball is thrown directly downward with an initial speed of 8 meters per second from a height of 30 meters. How many seconds later does the ball strike the ground? So we draw our picture, and here's our initial height of 30 meters, and it's traveling this way. And there's 2 ways to do this. It's very convenient if we say that downwards is the positive direction, and that where it starts is where y is equal to 0. So y final equal to 30 is when it hits the ground. And that means that v initial is actually positive, and delta y is positive, and actually the acceleration is positive because it's in the downwards direction. So we want to find the time for it to hit the ground. Now we also want to be careful here that when we write our equation, we can write it like this. So delta y is the same thing as y minus y initial. So we set this up, and we have 30 is equal to 8t plus 4.9 t squared. Now we're getting 8 from v naught, and we're getting 4.9 from a half of 9.8. So we have a quadratic, and we want to rewrite this so that we have, I'll just put it up here, 4.9 t squared plus 8t minus 30 equals 0. And when you have a quadratic, you want to set up a quadratic equation. So negative b plus or minus the square root of b squared minus 4a times c, all over 2a, which in this case is 9.8. And there's some pretty interesting things that you can see if you do this with just the variables, but we're not going to get into that just now. So it turns out that there's 2 answers to this, 1.8 and negative 3.4. We have to analyze this. Does it really make sense that it takes negative seconds for something to hit the ground? No. So our answer is going to be 1.8 seconds. Now the other way to think about this is that if I did a graph of y versus time, okay, and let's say that I put it like this, so that we start off at 0 and we want to get to 30. Okay? Well, turns out that when t is equal to 0, we're already on a downwards trend for our parabola. So this would be about 1.8 seconds. But there's a whole other part of the parabola that we haven't looked at. And that's a terrible drawing, so I'm just going to draw it another way. Okay, if we just think about distance, so the absolute value of that. We started off at 0, but with some sort of initial speed. And so really what's happening is that we have a parabola that has kind of 2 zeros. Okay, right here and right here. So we're going to have 2 answers for this function. Okay, so that's going to wrap it up for our first unit of one-dimensional motion. Next time we're going to start getting into motion in 2 dimensions, including projectiles.